For Lab 5, Choose Your Own Adventure, I'll be analyzing SpongeBob falling down to the sand of the town Bikini Bottom. I'll start off by showing you a clip of SpongeBob as he is falling down. Objectives. The objectives for this lab: to obtain real data from your own video, observations, or the internet. Use at least one physics model to predict something observed in your data, and use VPython as a modeling tool to predict physics outcomes. The initial calculations for SpongeBob. As SpongeBob falls, he is acted on by the force of gravity and drag force. We can ignore air resistance here because SpongeBob is falling underwater, and therefore there is no air resistance. That needs to be taken into account. Drag force is taken into account using the formula Fd equals vector 0, -1, -1 being because the force of drag is acting in the opposite direction, times the constant b, times the magnitude of ball dot valve, the velocity of SpongeBob, times the magnitude of ball dot valve, comma 0. After doing some research, I found that SpongeBob weighs approximately 1 ounce, which is approximately 0.035274 grams. So therefore, I set ball dot m being the weight of SpongeBob equal to 0.035274. Newton's second law is definitely important as far as analyzing SpongeBob's fall and taking into account the force of gravity as well as the drag force. To familiarize yourself, Newton's second law is the final velocity set equal to the initial velocity plus F net, the total pushes and pulls, divided by the mass of SpongeBob times delta t, the change in time. And also be looked at as the force is equal to mass times acceleration. The net force is 0 because SpongeBob isn't moving at constant velocity, which is shown in the video. So therefore we know that the total pushes and pulls are the summation of the force of gravity and the drag force, which is why in the VPython code we have F net equals to W plus Fd. Fd representing the force, the drag force, W representing the force due to gravity. Code for Newton's second law. Ball dot vel, which is equal to the final velocity, set equal to ball dot vel, the initial velocity of SpongeBob, plus F net, the total pushes and pulls on SpongeBob, divided by ball dot m, the mass of SpongeBob, times the delta t being the change in time. Ball dot position can be looked at as the final position of SpongeBob set equal to ball dot POS, the initial position of SpongeBob, plus his velocity times the change in time. These two things are used in the code when analyzing SpongeBob's motion. So here I was able to find the predicted motion after using the code, and you can see that the force of gravity is pointing down as well as the drag force pointing in the opposite direction as SpongeBob falls down to the ground. Now after analyzing SpongeBob's motion using Tracker, I was able to compare my predicted model versus my observed model's motion. And as you can see, there is some slight deviation. Now this was taken over an approximately 3-second interval because SpongeBob's fall was approximately 3 seconds. You can see there's a slight deviation here, but it's pretty spot on. The deviation though could have resulted because when tracking the motion using Tracker, I could have inaccurately clicked some tracks which didn't line up properly, which that would create deviation between the observed and the predicted model. So a question that I came up with that I felt like that would be very important towards this would be, how does being underwater affect potentially reaching terminal velocity? Well, for starters, terminal velocity of a falling object is the velocity of the object, in this case being SpongeBob, when the sum of the drag force equals the downward force of gravity acting on the object. So, when looking at this question, the key thing that comes into play is that SpongeBob is underwater. So when underwater, you have to take into account the buoyancy of the water as well in calculating when the object will reach terminal velocity. Therefore, depending on the buoyancy of the water, it will take shorter or longer to reach terminal velocity in water as opposed to in air. Thank you for your time.